Alrighty, it is 2 after, so let's officially get started and kick this session off. So thank you all for being here. My name is Sara Nash. I'm going to be moderating this really exciting discussion on semantic graphs in action, where we aim to let kind of battle lines dim down and talk through how LPG and RDF frameworks can work together, and also, most importantly, how you can best select the right graph approach for various scenarios. And so, this is a great conversation for organizations who are in early stage of understanding, knowing that they have challenges that can be well solved through connected data, where to begin, all the way to organizations who have been leveraging graph and semantics and analytics and want to really expand that to be more of an enterprise-wide solution to tackle multiple different use cases. So Sara Nash, I'm from the Enterprise Knowledge team. We're a consultancy that focuses on knowledge, data, and information management with a special practice in the graph development space. Joined with brilliant colleagues, Elliott Risch, James Egan, and David Hughes, who are going to be talking us through their real experience, the kind of background of labeled property graphs, RDF and semantic graphs, and kind of what's the best thing in various scenarios. Elliott has a particular specialization in semantics and AI. So he's going to be bringing that perspective to the table. James is our ontologist, and he has experience designing, graph data models in both the semantics and the property graph space. David is one of our principal solution architects, specialization in agents, AI, and a deep background in the labeled property graphs and graph analytics space. So you will learn more from each of them throughout this conversation. We are going to start with kind of brief background into these frameworks with the demo of how connected data solutions are built and work together, to kind of bring the concepts to life. And then the majority of the time will be discussion across our panelists, with time for questions from you. And so you'll notice there's a Q&A section at the bottom of our Zoom. And so if you have questions that you'd like our panelists to answer, then please throw those in there, and we will try to get to as many as that we can. All right, so without further ado, let's jump in. So want to orient you around, before we get into, what are these different frameworks, implementation considerations, what's the solution space that we're working in? And so here are 3 different scenarios that you might be faced with, and you might wonder, what is the right solution to solve for in each of these spaces? So for something like Customer 360, where you have information that's been siloed across many different information management, content management, data management systems, legacy, in the sense that they are really locked in their ways, and it's difficult to be able to see a kind of wholesome view of something like a customer. Another situation might be where you're looking to conduct investigations and really be able to build a network to understand, what is the connection between people and organizations and their activities, to help understand how organizations might be connected to identify particular threats. A last scenario might be where, an insurance organization is trying to understand where might there be fraudulent activity, and where might there be, people who are acting across multiple different accounts or something like that, where that information is siloed and not resolved. And so, what all of these, the kind of through point across all of these use cases is it requires connected information. It takes, it focuses on what the core concepts are and the relationships between them. There's, it doesn't really matter where the information is coming from necessarily. You want to be able to do sort of analysis and discovery in a connected way. And so we're going to talk through some of these frameworks and then see what would be the right framework to apply in each of these scenarios. So have these in mind as you're going through, and see if you would be able to identify what the right framework is for each of these. So to start, to introduce semantic graphs or RDF graphs, we'll use those kind of interchangeably for, compared to, traversal graphs or LPGs. They're really, it's not a matter of kind of one or the other. There's opportunities to leverage them both together, but certain, frameworks and tooling is best suited for particular types of use cases. And so we find that semantic graphs are really, strong in the sense of formalizing business context and being able to embed, business understanding in order to provide context for use in AI, provide context to agents, aggregating data and content. They're, I think, well suited for working with diverse types of information. So not just on the structured data side, but really content, unstructured information that has maybe some more semantic nuance that's helpful to capture along with them. And another real strength within the semantic space is around consistency and structure and real control over your information. And so these lend itself to use cases like providing 360 views, more natural language search and things like GraphRag, and enabling content discovery, structuring data products and things like that. Whereas on the right-hand side, traversal graphs or LPG graphs are really best suited for where visualization is an important piece of the puzzle, and being able to be kind of explore what the connections between different nodes in your network are. Traversal graphs or LPGs are more performant when it comes to analytics and using graph algorithms. They're best suited for that and most performant in that sense. And also for temporal information. So being able to monitor information over time, semantic graphs are best suited for kind of understanding your information at a certain time of need, where traversal graphs have the capacity to kind of track information more over time. And so this really lends itself to use cases where you really want to see the connections between particular things as a network and do kind of large scale analysis and pattern recognition in that sense. So this is really popular use case in the investigations or supply chain or fraud detection space. And as agents are on the rise, LPGs would be best suited to serve as your kind of observation in terms of understanding the kind of almost like supply chain of an agentic workflow. So my colleagues are going to jump into a little bit more specifics on the back end of what these work, kind of really constitute, and then we'll go into a demo and see how these different frameworks can ultimately work together. All right, so I'm going to go to the next slide. Turn it over to James here.
Thank you. So semantic graphs are like other graphs, a network of nodes and edges representing different entities in the world and the relationships between them, usually structured with a defined ontology or some other form of metagraph that's there to provide context and meaning to data integration, validation, and enable reasoning across different data sets. It goes beyond just simple data storage by explicitly defining the semantic connections between different data elements. These semantic graphs are usually all based on RDF, which is Resource Description Framework. RDF is a standard model for representing information about resources on the web. So resources here means just things in the world, the things that our data is about. It's a framework for describing and interchanging that data in a machine readable format, and follows a lot of the solutions to data distribution that were developed initially for the web in the first place. It's all organized in a simple structure called a triple, a subject, predicate, object, which you can see an example of over on the right. So Bill, the subject, has coworker, predicate, object, Janet. All the triple structure maps directly to how data might be stored in tabular data in columns and rows, where we're able to have a global reference for the row, for the column, and the value in the cell itself. All of this then enables things like inferring information that isn't explicitly stated in our data. So the example on the right shows an example of an inference where, because Bill and Janet are coworkers, and we know perhaps that one of them is employed by Acme. If they're coworkers, then they both are employed by Acme, even if that's not explicitly defined in our data. And now I'll turn it over to David to talk about traversal graphs and LPGs.
Thank you, James. So let's look at that same data that James was just showing us in a RDF model and look at it in a labeled property graph model. And so you can see here that the concept that Bill has a coworker and is employed by Acme, that those are still modeled just in a different way. You can see here in some of these relationships, some of the capabilities around temporally structuring the data and being able to traverse things based on time. But what are some of the key features and characteristics of a labeled property graph that are unique or maybe different than what we just heard from James? And one of the first things that really comes to light is that the data model itself is a little bit more lightweight. It doesn't have that formalism of RDF. That is both a blessing and a curse. It can be schema-free, but some of the newer technologies around labeled property graphs use a schema-first approach similar to what we see in RDF and other implementations. There is advantages for doing that. And then finally, the LPG domain is really optimized for particular use cases. And that is where you need to do a deep traversal or following those relationships as first-class citizens throughout your data to really surface that insight and the signal that is generally latent or hard to find in relational data. It is optimized for analytics, and then, of course, for graph algorithms and machine learning. We find that LPG in GraphRag also is a great complement to looking at vectorized data. Let's look at the next slide. And so with that in mind, what are some of the use cases for both the RDF solution that we've heard about and the labeled property graph that we've looked at? And is there a world and a use case where a hybridized approach might be best suited and fitted for what you're trying to do? So we looked at the beginning. Sara was talking to us about Customer 360, and that really is the domain of a semantic graph because of that integration of all kinds of different data, structured or unstructured, being able to formalize the relationships between the entities in that data so that you can then perform semantic search, as we saw in the earlier slides. Now, in a use case where you actually want to do investigation, for example, one of the ones that we saw, then being able to perform analytics and actually materialize a single pane of intelligence of what is happening in those relationships between entities. This is the domain of a traversal graph or an LPG solution. It also helps us understand what are the trends that we're seeing developing or the patterns and clusters of data that we can reveal in that connected data. So with those in mind, if we were to hybridize them and bring them together, what we are going to see from Elliott in a demo coming up shortly is that by consolidating that data, we can actually look at through the lens of RDF and LPG and start to do inference on data so that we can actually make claims that aren't actually stored in the data, but are inferable. We can actually perform advanced analytics and surface potentially fraudulent activity if we're looking at a fintech use case. And then finally, by looking at the inference capabilities, we might expose high-risk synthetic or high-risk issues that weren't able to be exposed in either a semantic and or traversal approach. So this is a good time now. I'm going to hand off to Elliott, who's going to walk us through a demo looking at this last use case where we are hybridizing and creating the intersection of RDF and LPG. Elliott?
Perfect. Thank you so much, David. So in this last case, there's something in the background of all of this, which is that historically, RDF graphs and LPGs have been in a sort of war where so a client wanted to adopt a graph solution and they felt like they had to do one or the other, and that in the end, what they wanted to do was replace where their data lived originally in structured data in Postgres or other sort of SQL databases. What we want to show right now is that because of the difference between the two different graph solutions, they actually kind of allow us to form a circuit that ends up starting in the structured data, integrating in the RDF, allowing for additional facts to be inferred and validated. And then that in turn allows us to export really clean traversal graphs that allow for really powerful analytics and the inference of new features that can then be fed right back into where the data is stored and pulled back into the RDF. What this loop forms is an ability to create two kinds of reasoning that allows you to take data that was kind of spread out and kind of wasted before, bring it together, infer it on the basis, or infer information on the basis of what that data means, and then also look at some really, really deep patterns that emerge in that data when we can look at it at scale, and then start again. So to demonstrate this, I'm going to share my screen here and run us through one such loop. So let us start the pipeline. So what we have here is I'm going to generate some multi-source data. I'm going to generate 1,000 people, 221 cases of 8 different unique diseases. So I have some samples here. So we have a few people here. We have a few cases here, the date that the disease was onset, the different diseases that are sicknesses that we have identified. And then down here, we have some like relationship information. Specifically, we have person-to-person contact information and when it occurred. And these persons, these indexes refer to people up here. And then we have some travel history of where people have been visiting. So we want to be able to use both of those additional relational information with the information above to start creating a more robust picture, presupposing some meaning. Because right now, we don't know that person ID 0 and person ID 0 here mean the same thing, and that that person has COVID and someone with COVID went to visit Lake Nicoleview, which is a byproduct of how I generated this because it's all dummy data. So let's go over and let's take all those different sources and start blending them in to one big knowledge graph. So we take all four of our sources, 2 from Postgres and 2 from that CSV file. Want to verify the integration, good. What kind of comes together when I pull all that information together is 36,000 different facts, right? Some of it's coming again from the Postgres, some of it's coming from the CSV because it's not even going to necessarily be in the same format. It could also be like multiple different Postgres databases. And we want to show what I've essentially done over here is I've assigned a unique identifier to each person and to each predicate. And that allows us to resolve the people who might have been stored in different locations together. So when I refer to one person in one database, I refer to them in the other database, that my graph can see them as the same thing. So now that I've done that, and I have my people, let's do a little bit of reasoning. So beforehand, here, let's start the reasoning because it takes a second. I've defined the domain of this use case, right? So I have defined person as a class, case as a class, disease as a class, even city and cluster. I have high risk cluster because in the end, what I want to do is I want to identify people who are highly at risk of having contracted one or the other sickness, right? So I've defined what a healthy person is, what an unhealthy person is. This is what we call an ontology, right? And this isn't that complicated, and it can be used to support this use case, right? Because at the end, what I want to be able to do is I want to find the high risk people. I can also find the high risk healthy people, but let's put that to the side for now. So after semantic reasoning, I started with 36,000 facts, a little bit more, and I've inferred 26,000 additional facts, leading to 62,000 facts in total that I can now ask questions against. Some of these inferences are things like type relationships. I might have inferred that someone was a person because of the sort of relationship they had. I wouldn't have to hard code that into the extraction. I've also collapsed a lot of the people into being the same person, right? A few things that looked like they were different, I said, oh, because of these characteristics that they have, they're actually the same thing. So we've resolved some of our entities. But the next thing we're going to do is I want to close some of my shapes, right? What the reasoning here relies on is the open world assumption, which doesn't make claims about things it doesn't know. What I want to do is say for some of the data shapes, the information that we have is all the information that's relevant. And so I want to figure out what the actual like closed shapes look like. And for that, I'm going to use one of these, I'm going to allow for shackle validation. This will give us a really clean data set that I can then export over and do my network analysis on. Because in the end, I want to do all this data curation and data wrangling up front. So what this has resulted in is 7 node shapes being validated against. 0 warnings showed up, so that none of my data has broken from the shape that I wanted to be in. I have identified 0 high-risk individuals, but I have identified 221 unhealthy individuals. So we could stop there. We're not going to for the purpose of this, but at this point, we've integrated our information and we can ask some really complicated questions at this point with fairly simple queries. So for instance, we could ask the top travel destinations for people with COVID-19. And don't worry about the sparkle. A lot of what we're doing with semantic RAG essentially offloads the consistent creation of sparkle to agents who you ask questions in ordinary language, questions like what were the top travel destinations for people with COVID-19? And it creates this for you and will give you information like this. So East Courtney Chester was the top travel destination for our individuals with COVID-19, leading to 5 visits. So we could stop there, but the powerful thing is to be able to take subgraphs from this larger graph that we've already done all the data wrangling for and export them for additional analysis. We can do that by exporting labeled property graphs. So that's what I'm going to do here. In this labeled property graph, I exported my 100-person nodes, and I have also exported all the relationships that can hold between them, right? And what I'll do next is I'll do some clustering out, or I will run a Louvain clustering algorithm over them to identify what the highest highest density areas were. So that went quick, and we can see everybody's been assigned to a cluster, and we can see that these are the 3 highest clusters. Now, this would be a place where we would inject a lot more information if we were immunologists about like what we wanted to actually understand as like being high risk. For me, I was just like the 3 most dense clusterings are going to be the highest risk. So I'm going off of that. But what I'm going to do here is instead of writing it back up to the RDF database, I want to run it back to the relational database where the records live. What this allows me to do is it allows me to drop the graphs at any point. Maybe I store them, maybe I just drop them completely. And then I can write my information back into those graphs from where that information actually lives. Sometimes we'll go in and clients will, specifically their DevOps team, will be very worried about all the additional movement they're going to have to do, or like how they're going to have to get rid of their old relational databases. These actually, in a lot of ways, work better when you keep your original relational databases. So I'm going to now reload and re-infer information coming out of those relational databases with the additional inference, which allowed us to create the more robust label property graphs, which then allowed us to make a more robust set of connections and an identification of the clusters, which were then read back into the relational database and now are being put back into the semantic graph so that they can be re-inferred upon. So you can see it here. We're now coming back around and going back up. Additionally, we can watch everything that's happening. So if you did have an agential system or agentic system, you'd be able to use those agents to kind of monitor what's going on. So here we are. We have identified a few sample high-risk clusters. They're 0, 1, and 2. And here are some individuals that end up belonging to those clusters. So let's run that back. This is going to take just 1 second. So if any of my colleagues want to chime in at this point, this would be the best point to do so.
So just to re-clarify, you've taken the RDF data that has been both validated using things like Shackle, that you created some initial new insights from inference, and then you loaded that into a labeled property graph so that you could do a graph algorithm. And in this case, you were doing Louvain for clustering, and then you were able to then actually re-enrich the original RDF data by creating this round trip loop. And I see you have some results. So what did we find?
Yeah, we found 313 high-risk individuals. We can see what they would look like down here. This is just a sample of a few of them. So like person 459 and so on and so forth. We could use this for additional classification. We could imagine a situation where maybe once we've identified them, we would send them an email and tell them like, hey, like you've been flagged as maybe possibly coming into contact with someone. Maybe you should go to the doctor, so on and so forth. And this was, this is a toy example made up for one particular case. These are all generalizable patterns that we could use elsewhere. When we originally came up with this pattern, it was in a fraud detection case where we used graph algorithms to spot hotspots that might be like potentially fraudulent actors. And then we exported those back into the relational databases as things to investigate. And then they would move them over and like send investigators out to go do some more traversal, which would be another thing. Once you have it in the relational database, you could export it back into a label property graph and start looking around. So like, because you have all of your records or your data of record in the relational database here, you can kind of freely move between the different views. And that's one thing that we might think of is like the graphs are a way of viewing your data, and they're two different ways of viewing the data. So we're done here. I'm gonna send it back to my colleagues.
All right. Well, I see there is one question we have from Javed in the chat, which is how long would it take to run the mentioned reasoner for 100 million triples? So would you use a different approach when it comes to doing reasoning at scale? And while you're pondering on that question, I see we have a hand up as well in the audience. And so if you have any questions and like to contribute, please use the Q&A function, and we'll get to questions in that way. And so if people have some questions on the demo itself, please kind of bring those in now, and then we'll answer this one, and then we'll go into our broader discussion on this topic area. But Elliott, do you want to take Javed's question here?
Yeah, definitely. So for the purposes of this demo, I stuck with open source libraries using Python, specifically RDF-lib and NetworkX. So this is not the level of performance that I would expect in production. For that, we have a great number of different companies that we work with who hopefully we'll talk more about later on. But yeah, so at scale, you'd want to be doing this with like multiple cores and not on my 16 gigs of RAM on my MacBook. So yeah, but yeah, at scale, it would really depend. If you needed it to happen nearly instantaneously, that would be a matter of compute, not a matter of whether it could or not. It would just you'd have to pay for it to go faster or slower. If you could do it overnight, that's another way to do it. But for fast iteration over and over again, if you needed to run it constantly, it would just be a matter of scaling your compute.
Awesome. So I want to kind of ask two questions that are in the context of this scenario of the demo. And first, to you, David, which is that let's say an organization were to take this solution space around, doing, tracking the disease evolution over time and things like that. If an organization were to say, cut out the RDF step and just go directly into the LPG as that first starting point, what would be the advantages of that, and what might they be losing out on if you were to take out that staging space?
Yeah. Well, I think that it's not necessarily, in my opinion, advantages. It's just where you're putting effort and what capabilities you end up with. By removing a RDF step, then are going to have to be more thoughtful about potentially a schema first approach in your LPG, just to ensure that you have good structure that downstream analytics or agents are going to be able to take advantage of in a deterministic way. But what we're finding is that the loss is really that semantic enrichment for the labeled property graph and those downstream actions. So the intersection of the two, I think, is the hybrid approach that Elliott showed us is going to be where we see on the horizon more and more activities coming. There used to be a big gulf between RDF and LPG, and what we're finding is, to use a meme, I guess, better together.
That's great. And James, from the perspective of the kind of the opposite side of that question, if you were to work in that solution space, build a semantic knowledge graph to track the information within this demo, what kinds of things would you be able to unlock in that step? But what might be more difficult, or what might you be missing out on if you didn't also kind of render an labeled property graph?
Yeah, I think you'd be able to select data from many different resources. I think the value of semantic graphs is it's able to align data that's stored in different servers and different formats, and sometimes even different languages entirely. And wherever that information is distributed, it's able to merge those together in a graph aligned to vocabulary like an ontology, which enables decidable reasoning about that data. In the labeled property graph, some of that semantic enforcement is lost, and some of the ability to perform that decidable reasoning and control. Essentially, this is our understanding of the things that our data is about. That switches over to more the ability to link things directly together without the structure of the RDF triple structure in the first place. So I think using them together, you get more performative graph with the labeled property graph, since some of the limitations of RDF by structuring everything in triples means that each statement about something has to be a one-to-one relationship. And for example, in an LPG, you're able to add properties for those relationships itself. So an RDF graph is going to just expand and expand and expand and get much bigger and harder to query and take up more processing time, whereas an LPG graph is then able to perform some of those queries in a much more efficient, quicker way.
Awesome. Thanks, James. And so next I want to kind of zoom in on developments within AI and the agentic space, and how do we see basically a major new consumer of graph data being agents, or being other kind of AI frameworks. And so I'm curious, how does that influence the decision making on what kinds of tooling and approaches organizations should do when they're looking to build their connected data ecosystem? Let's start with Elliott, and then David, would love to hear your perspective on this one as well.
Yeah, thanks, Sarah. Yeah, there's a variety of them, but one thing I'd like to call out, and it goes to Glenn's question from the chat, uh, is a pattern that we've been working on to kind of get around having to embed and re-embed all of your documents, but instead create document graphs that you can then tag on, and then hold particular documents as nodes, not holding any of the text, but relating them to particular tags so that you can run queries over your documents using those tags and find a smaller subset of documents to then go retrieve at the moment of query and do them, embed them in memory and provide them to the agent within the context of the document. Something like, hey, this person asked this question triggered this graph query, it returned these 8 documents. We parsed them, ran rags over each of them individually in memory. And here's the most relevant chunk from each of these documents. And then allow it to answer and synthesize between the information provided within the context of those documents without ever having to move the documents from where they exist. Maybe they're in a SharePoint somewhere where the API call number was one of the attributes on the node itself. So that's one of the ways that we've been dealing with unstructured information. Another approach would be to actually break up the unstructured information itself into a graphical representation of it. This is especially relevant if you have highly structured data. And we could talk more about what that looks like too. But really, to kind of make this short, I think that one of the largest impacts I've seen is in the integration of your content worries and your data worries into a single view. So not only are we seeing a lot of integration between RDF and LPG in the solutions that we're thinking about, but also between content and data, putting them into a unified view so that when you're providing context to an agent or a series or system of agents, that all that information can kind of be provided to them within the same language.
That's great. And David, would love to hear from you on this question of, how developments in AI are influencing how and, how to go about building your connected data ecosystem. And I think we can tie in a question that we had from the audience too around how does it relate into hallucination reduction? So give us your perspective on this and especially through the lens of reducing hallucinations.
Yeah. The semantics that you can get and the topology and the understanding of your data that you get from LPG, the semantics from the formalisms in RDF are really well suited for today's agentic workflows, whether that's just an AI workflow or a full agent workflow. The what we're seeing is the evolution and the development of the concept of a semantic agent. And that is language models have been trained on various different distributions of data, and they may not always understand a enterprise's unique set of information. They may be able to make some claims against it and some inference, but not generally the specifics of, say, something unique for drug discovery. Having a semantic agent that is using an ontology and a taxonomy, but then also leveraging the actual topology of the data, how things are linked together, and being able to traverse that very deeply is what's going to empower an agent not only to retrieve rich results in this graph RAG approach that we hear so much about, but then also leverage the semantics from the ontology so that it is able to uniquely reason on that information. Now, to hallucination, it all is integrated into what I was just saying in the sense that if a semantic agent has the capability to look at its results, it understands the actual ontology of the domain that these results are for. Let's just go back to drug discovery. And it is able to look at the user's request. It can do an evaluation, or you can have an observability and evaluation framework running externally that's looking at both the user's input what context the agent had, and that is both the graph results maybe from LPG, the ontology and the semantics from RDF, and then the answer. And this evaluator, whether that be a language model as a judge or a human in the loop, that is where you can start to develop metrics and evaluations on things like hallucination, usefulness. What is the recall of the context that the agent had and used in those operations? So I did see another question, if I may, Sarah, about there was a question from one of the attendees on does the solution or solutions like the one that we saw require more tooling now? And there are open source solutions. There's embeddable approaches. There are ways to look at data at rest through lenses that are like graph, but without having to move things around. There's many different approaches, and so the answer, as most always is the case, it depends. Sometimes more tooling for performance and for a particular use case absolutely makes sense. Sometimes where the use case is amenable, there's some newer approaches that are worth exploring.
That's great. And David, while we're on that question of what kind of resources are needed, and I will say, I know the answer is going to be, it depends, but could you talk a little bit more about the broader set of considerations and resources from both the tooling perspective and from the kinds of people or skill sets that need to be involved and prepared to build out solutions in this space?
Mm-hmm. With the capability that we are seeing mature almost meteorically right now, there's been a lot of talk about, well, couldn't you do all of this through generative AI? And while there are a lot of capabilities to do that, you still need specialists because I think at most what we'll get is a bootstrapping from some more of these Gen AI approaches. And ultimately, at the end of the day, it takes the expertise of subject matter experts. You need people like James who understand the rich formalisms and then of course the advantages that come from that when you develop an ontology. You need an AI engineering team who understands that language models have an inherent distribution of what they were trained on. So having semantics being able to enrich their ability to reason on the results absolutely makes sense. And then there's things that have never gone away and won't go away, and that is the concepts of things like ML ops, or now it is AI ops. And having a complete workflow for being able to orchestrate and host and manage the systems that take advantage of semantic graphs and traversal graphs. And then finally, I would say, Sarah, that first and foremost is having an observability and evaluation framework that allows both the enterprise and then all the way down to the developers the ability to inspect what is happening with data retrieval, semantic enrichment, and then ultimately answer and response back to a user, and being able to inspect, evaluate, and optimize those in real time.
Awesome. And James, I have a question for you. And I know this from personal experience, as I know one of the like engagements that you're working on, you're working on building out an LPG graph, a graph that's primarily meant for investigations, analytics around the relationships between people and organizations, and yet there's a really important ontology design component and taxonomy design component that is, traditionally more associated with the RDF space. And so it's this interesting hybrid where you can pull some of the frameworks and best practices around modeling and control within the semantic space, but apply that into this more analytical environment. So could you talk us through a little bit what your approach is, how you've gone about, bridging those worlds in that scenario?
Yeah, definitely. So I think there's always two considerations with semantics and graphs like this, is that we want our information to be understandable and exchangeable across different sources, both to humans, but also we need it to be machine readable. The rich formalism from a lot of the semantic web standards, the languages and frameworks beyond RDF, like RDFS and OWL, as well as Shackle, which Elliott showed, as well as standard foundational ontology vocabularies. In this example, we're using basic formal ontology. The value of that is it is using something like OWL and OWL reasoning that allows there to be a decidable fragment of logic built over your data and within the solution. But on the other side, there's a real need for users to be able to navigate and directly interface with the graph, in this case for viewing investigations and understanding information from different sources in a direct application dashboard view. So in this case, the semantic considerations are a little bit different in that they need to be understandable to the users and they need to be intuitive, and they can't be so complex that they favor the underlying machine logic over the experience of the user. So for this solution, we've been able to map two different vocabularies together where we have a much fuller, extensive, complicated OWL-based ontology that's able to capture data from across the organization. And then we're able to then take fragments of that and slices of it for a particular application and map it to another schema that is then directly experienced by the users within an LPG-based graph.
Excellent. Thanks, James. Super helpful. And we've been getting some great questions in from the audience, so really appreciate them. Keep them coming. We have time to answer a few more of these. So want to narrow into this question around, and I think this has come up in a couple of other questions as well, which is around data storage considerations. And in this particular demo, which was meant to kind of show the kind of flow of information, it requires copying of data, multiple storage places. And so there's a question around how might you solution in a way that doesn't create copies of data, but to kind of consume and update in a single location. And so I'm wondering, see, Elliott came off mute for that, get your thoughts here, and maybe David, if you have thoughts as well.
I'll let David go first, actually, on this one. Because
All right, thank you. So that's a great question, and these are questions that we hear from clients and certainly we see in the profession in communities. There are, as I said, it depends on your use case, but there are approaches that we've either developed internally and have explored, and we're also seeing others in the community explore as well, and clients. For the ability to perform semantic enrichment and some of the capabilities of RDF, as Elliott demonstrated, you can do those in a embedded system or as part of an in-memory system. If you needed to do it at scale, this is where I start to think about either some of the newer capabilities of Network X and being able to have a single code base that runs on CPU versus GPU. For at-scale inference, I look to things like Ray IO and some of the capabilities for distributed compute there in a very Pythonic and approachable way. And for the data that is still at that point, either in relational or in a memory format, that memory format is both graph in nature, but you can also query that through an LPG lens using some of these new graph query engines. So there are some techniques out there to do much of what we just demonstrated, either all in memory or using graph query engines. Elliott, do you have anything you'd want to add for additional enrichment?
yeah, so I completely agree with everything that David said, and I will add, and this is kind of represented in how the practices at Enterprise Knowledge are set up. But there are two major questions that you want to ask when you're going into a graph solution. One is, how do I want to model? Because there is no perfect way to model. It is always going to be attempting to capture a perspective on the world, not just the world. If you try to model the world, that ends up a problem every single time because there's different perspectives on the world. So there's the modeling question. Then on the other side of things, we have a engineering question, a semantic engineering question of at what points am I going to ask questions? What sort of graph needs to be there at those points? What sort of resources are going to pull on that graph? And what does the life cycle of the graph need to look like? So defining the life cycle of the graph is just as important as modeling. And these two things work together because modeling considerations will have considerations on life cycle, and life cycle will have considerations on modeling. And they're kind of in this loop, which is why we have these two practices that work together very closely. So for instance, James is from semantic modeling. I'm from semantic engineering, and so is David. So we are having these conversations constantly. And again, it's always going to be different because everybody has a different reason that they're connecting their data, and they have different needs for when they need to be able to answer questions and how fast and how current. And these are all things that we use when we are evaluating use cases with clients. So.
Awesome. All right. Well, I want to pull another question. This one be for James, which is that so given that LPGs have no shared semantics around them, is it harder to merge different data sources? So does it mean that you can create something that's great and robust, but ultimately is isolated because there isn't that shared semantic meaning?
Yeah, so this is part of the challenge of working with distributed data in general, but within graphs is how do we know that a node in one graph is the same as a node in another graph? And how do we know that two different nodes might actually be identical to each other? So the RDF solution to this is resolved through the use of uniform resource identifiers, where there's a unique ID that looks like a web address for every single element within the triple store and within the graph. To do the same in an LPG requires more of a custom approach because there's no explicit semantics that come with it and are built in within a framework like RDF. But similar approaches can be adopted there as well, where you can have unique IDs for each of the different nodes in the graph, and you can do use different tools and approaches for entity resolution to understand when two different nodes are actually the same and should be merged together. And when you have two different graphs that overlap together in similar ways, in a similar way, you can also then incorporate relationships within the LPG that can enforce a particular schema or map to something like your ontology.
Excellent. Thanks, James. All right, I'm going to ask, I think one last question here, which is, one of the benefits that we have is that we're able to work with many different organizations who are able to work across, different industries, different sets of maturity, and so use that kind of pulse on the industry and sense of like to build a sense of what the trends are and where things might be going. And so I'm curious for our panelists, what do you think, where do you see this space growing into the future? What are, we've taken the steps to start to bridge some divides across LPG and RDF camps, which is one stage, but where do you see the kind of the future in terms of, a more connected, truly connected graph environment as we move forward?
I'll jump in and say, I think that we'll stop having webinars and conversations like this because the implementation won't become necessary a point of contention. It'll be more around how do we look at our data through a semantic and connected lens. The underlying approach, I think is going to become more around just the implementation, but the focus will shift to how do we empower both agentic AI and still human in the loop workflows that can take advantage of these capabilities, regardless of how the or where the data is. We're seeing a lot of work and evolution in lakehouses for the storage of source data and a lot of capabilities being applied directly to that data at rest. That's what I think is on the horizon, is being able to work on a single copy of data, but through various different lenses.
I guess I'll go next. So I see the possibility for in the future a move towards uncoupling the data stack, where a semantic kernel lives in the middle of your all of your resources, and you are allowed to read resources through that kernel on the basis of what entitlements you've been allotted to. What this would allow for is for the cultivation of hierarchies of contexts. So like context for projects, context for meetings, context for tasks that allow us to very carefully dole out information so that agents and humans can interact together with a shared background set of assumptions. And to handle those sorts of contexts, we will need to be able to freely, but on the basis of permissions, pull information that has been integrated from a central source. And what a semantic kernel would allow for is it would allow for information to be plugged in and out of that kernel. And the only thing that would remain the same over time is what the meaning of your information actually is.
Excellent. All right. Well, with just a couple minutes left, James, did you have anything you wanted to add on to that?
No, I think both David and Elliot said it well.
Wonderful. All right. So I want to thank first and foremost our panelists for their time and really their like deep experience and appreciate that they, are able to share that out to the broader community here. And for all the attendees for joining us today. It's the one thing that's unfortunate about this webinar environment is we are not able to hear kind of your stories and the like examples and kind of practices that you've been seeing. But there is an opportunity to kind of bring some of those things into real life. And so just want to briefly share that we have a symposium coming up this October in Copenhagen, the Semantic Layer Symposium. This is the second year of this event. It's a wonderful like opportunity to bring together practitioners. There's no sponsors, no sales. It's really an opportunity to have more of these kinds of conversations. There's going to be a full day workshop on the first day where on the last day of September, where we are going to do more kind of background in the semantic layer space, an enterprise simulation of building a graph end to end within the workshop, and then a really wonderful like set of talks on October 1st. So hope that you can join us. There's a QR code here. And we will be sending out the recording for this. If you have any additional questions or want to talk further, you can reach out to the EK office and would love to connect in that way. But appreciate your time and